Hi everyone, in this video I'm going to talk about diagonalization of matrices. And this one I'm not going to talk much about the theory, I'm just going to show you the mechanics of how to calculate this and what the problem is. So diagonalization means given a matrix A, a square matrix A in Rn by n, we want to find matrices P and D such that A equals this decomposition, PDP inverse. The main property that's of interest here is that D, this D in the decomposition, is in fact a diagonal matrix. So I'll just go through a simple example here of how you're going to calculate this. So the theory is built on the fact that P has columns which are eigenvectors of A. And the entries, so the entries D are made of the eigenvalues along the diagonal. And that will, if those are true, then the proof of this theorem actually says, basically shows that this holds. If P and D are defined that way. So how do you compute the eigenvalues and the eigenvectors of a matrix? Once you know that, you implicitly then have a diagonalization. So the way we do that is recall the definition of an eigenvalue and an eigenvector. So this is what an eigenvector means. It means that the vector only gets transformed by, it only gets lengthened or shortened or reversed in some, according to some scalar lambda. Where here x is non-zero, because x equals 0 is a trivial solution. It's always going to be true. Okay, so how do we solve? So we're looking for non-trivial solutions here. So as an algebraic trick, I'm going to rewrite this lambda x as lambda ix, where I is the identity, right? Because the identity times any vector just gives you back the same vector. And then I'm going to subtract on the other side. And we're looking for non-trivial solutions to this equation here. So since we are looking for non-trivial solutions, the invertible matrix theorem tells us that the only way that those solutions exist is if the determinant of A minus lambda I is 0. So let's compute that determinant. So A minus lambda I just looks like this. If you don't follow this algebra, just remember this is what A minus lambda I looks like. You can pause the video here if you need the algebra to go a little bit slower. Just make sure you understand what I'm doing here. So then this is equal to, right, so notice here for this matrix, these two entries are 0. So if I expand my 3 by 3 determinant along that row, I only have to multiply this by the determinant of this. So this is equal to 1 minus lambda times the determinant of minus 2 minus lambda, 1, 0, 3 minus lambda. And the determinant of this is actually just the product of the diagonals here. So this is 1 minus lambda minus 2 minus lambda, 3 minus lambda equals 0. So that's a nice form. That's very easy to solve for lambda. It has 3 roots already factored out for us. So I'm going to write lambda 1 equals 1, lambda 2 equals negative 2, lambda 3 equals 3. And now, so I have the eigenvalues. So the eigenvalues have been computed. That makes the matrix D. So now we need to compute P. So what we do is we plug if we call this equation star, then all we do is we plug each of the eigenvalues back into star. So so for lambda 1, go back up here. So we're looking at this equation here. So this diagonalists give us 0 because lambda equals 1, -3 because lambda equals 1, and 2 because lambda equals 1. So this is going to be 1 minus, so 0, 0, 0, 1, -3, 1, 0, 0, 2. All of that's equal to 0, so I'm just solving this augmented equation here. That tells you that x3 is 0, that x1 minus 3x2 equals 0. So I'm going to pick my first eigenvector v1. So notice here that I have one free variable. That's usually how this should work out. If you have two, you can have two free variables, but you should always have at least one free variable to pick your eigenvector. Which makes sense because you're looking for non-trivial solutions. Right, if there's a unique solution, you don't have free variables. So you should have at least one free variable. You might have more in general. So I'm going to pick v to be equal to, so 0 in the third component, 1 in the second component, and 3. That satisfies those constraints. So that's my first eigenvector. As for my second eigenvector, I'm going to subtract -2 now. So 1 minus -2 is 3, -2 minus -2 is 0, and 3 minus -2 is 5. 1, 1, 0, 0. Well, that's equal to 0. So that tells me that x1 is 0, x1 is 0, x3 is 0, x2 is free. So I'm going to pick v2 as 0, 1, 0. And then finally, lambda 3 is 3. 1 minus 3 is -2, -2 minus 3 is -5, and 3 minus 3 is 0. 0, 0, 0, 0, 0. So that tells me x1 is 0, -5 x2 plus x3 is 0. And so I'm going to take v3 to be equal to, the first component is 0, and I'm going to take the second component as 1, and I just have to make sure that I pick the third component as 5 times the second component. So P has columns given by this. So notice, and D is lambda 1, lambda 2, and lambda 3. So P, all written out, is 0, is 3, 1, 0, 0, 1, 0, 0, 1, 5, and D is equal to 1, -2, and 3. Zeros everywhere else. And so the last thing I'll note is that this order, so notice that the order doesn't necessarily matter as long as it is consistent. So this eigenvalue corresponds to this eigenvector. This eigenvalue corresponds to this eigenvector. And then finally, this eigenvalue corresponds to this eigenvector. Now, I could, if I want, flip these two. But that means I also have to flip these two to get the right answer back out. And there you have it. That is, you can check if you'd like. either by hand or via Wolfram or something like that, that A does indeed equal this matrix decomposition. Thank you.